All right, so this is some recent work we've done. That means mostly my students have done this, and I just made them do it. That is Kenny Di Stefano, who is about to defend his dissertation later this semester, in Zara Shabani. And this is about taking a stochastic system. So we're really not talking about mean field reaction diffusion equations, but we're doing this kind of stochastic, say, population dynamics. We set the system sufficiently small and unstable so it would get extinct just through stochastic fluctuations, so hitting its absorbing state, and we're stabilizing it by diffusive coupling with a stable system. And I thought this might be a fun application of these simulations and also of general interest because I think it's quite generic mechanism. So I'm going to briefly look at the stochastically spatially extended Lotka-Volterra model for predator-prey competition and coexistence, and then also some epidemic models. And the last reference is a preprint we have on this. Okay, so Lotka-Volterra, I'm sure you've seen this before. So we have predators, as I was explaining before, that left alone just die with a death rate mu, prey that give produce offspring at a birth rate sigma. This is asexual reproduction, so they just proliferate. And if you leave these alone, these die out, these take over, so you get prey fixation. And we control that by a nonlinear reaction that couples them. So whenever these two meet in space and time, as I emphasized before, the predators will eat the prey. So bad news for the prey. The predators just had a nice lunch, so they immediately reproduce and replace the prey particle by a predator individual. You can split that up, doesn't matter too much in the stochastic simulations, but that is the simplest version. And then on the mean field rate equation description, where in the second process, we are factorizing this kind of joint moment into just the densities, we get these famed Lotka-Volterra coupled ODEs, which allow for a conserved quantity. So that's just the first integral of these that is conserved in time. And so that means that I need to see oscillations, right? So if I have kind of this two-dimensional phase space and there's one conservation law in there, I'm running on a periodic orbit. And that's all beautiful. Has two downsides. Well, first of all, these kind of coexistence steady state isn't actually reached. You just take these orbits around it. But that conserved quantity has no physical background. It's really just an artifact of that factorization approximation. If I go back to my original stochastic model, it is not there. And so the question is, do these, famed population oscillations actually survive? And what happens to that if I put that on a stochastic spatial setting? For example, if this is really just kind of fine-tuned to this set of differential equations, then if I modify my model mildly, it behaves very differently. And so it's not actually robust. And so as I was trying to say before, this is violating the robustness principle of modeling. For example, if I have a finite carrying capacity, so as we were just discussing, if I restrict the total number of particles locally, say to this number k, then let's do that just for the prey birth process on the mean field level. I would put this logistic term in here, and that changes the phase diagram. We would actually not have these persistent oscillations, but instead we get a separation of an inactive state where prey fixate and predators go extinct to an active phase where both coexist. That is induced by that finite carrying capacity, or finite, in my case, then local restriction. And in that situation, I can have a nodal fixed point in these mean field equations. So we get exponential relaxations to that stationary state, which is now stable, or a focus where I get kind of oscillatory behavior, but damped oscillations. So that would be that system. But now we want to view this as a stochastic spatial system. If it's stochastic, we need to understand that any kind of coexistence in principle is transient. The system has an absorbing state, either only prey, it actually has two absorbing states, either only prey or everyone goes extinct. And that will be reached at some finite time. But that time, as I was saying before, tends to grow exponentially with system size. So it may not be relevant in any kind of typical experimental or simulation time, but it's there. And so when you do the agent-based simulations I was describing before, say on a two-dimensional lattice with periodic boundary conditions, and say k is 1, so we only have one particle per side, then what you're seeing is, as we have that restriction, the total particle density is restricted to 1. So we're living just in the lower triangle of this phase diagram. We actually see kind of the qualitative features of that mean field description. We see an actual phase transition. It's now a multi-dimensional, degree of freedom system with a real phase transition in the kind of mathematical physical sense, which is an absorbing state transition. The predators go away. Once they go away, they cannot recover. So this one is where we get prey fixation. Beyond that, we have coexistence, initially with this kind of exponential relaxation. So if we start with this initial kind of configuration, in time we run here and stop there. But as we increase the predation rate, make the system more nonlinear, if you like, but also go deeper into the predator-prey coexistence regime, we get these oscillations, damped oscillations. So we get this kind of focus-like structure. But if you look carefully, you see in that focus, it's not actually reaching that fixed point. The stochastic trajectory is always kind of stay away from that fixed point. And what happens there is really that demographic stochastic noise, which is just reaction induced, just the fact that we talk about stochastic processes. Down here, you can essentially map the system back to an oscillator, like in these mean field equations. It's an oscillator, it's a nonlinear oscillator, but you drive it now with random noise. Initially, that's demographic, it's multiplicative, but deep down in this coexistence regime, the typical mean densities of both predators and prey are finite. That changes this multiplicative noise effectively to just additive white noise. And so you have an oscillator that you drive with white noise. On occasion, you find the resonance frequency, give the system a large amplitude deviation from its stationary state, then it tries to exponentially relax back. You kick it again and keep going. So somehow deep down in this active state, far away from the actual phase transition, we find enhanced stochastic fluctuations, and those are not going away. In the spatial system, the way that looks is in one dimension, this is my world lines again going down. From an initial kind of random distribution of A and B, I get the species segregation effect. I get red domains, blue domains separated by the regions where this predation reaction happens. And then the red guys, can just entirely eat into these kind of blue triangles where the blue triangles are prey proliferating into empty space. Then the predators can invade one of these triangles and just eat that up. When that happens, they just stochastically die out, leave some black space behind until the blue guys come in again. And so you see this kind of triangular patches, if you like. In 2 dimensions, that maps into spreading reaction fronts, where prey again proliferate into empty space, are followed by predators, leaving behind some empty space, which the prey can invade, and you get these periodic fronts moving in there and back and forth. And single of these fronts you can describe by reaction diffusion equation. That's kind of the typical invasion fronts you can cook up. But this is still a fundamentally stochastic effect because you need random survivors that are kind of patched throughout the system and keep going. And then, of course, at some point you get these interactions. So what spatially happens in this regime here with these large blobs in the coexistence state is that you have ever ongoing moving fronts to your system, a very correlated non-equilibrium steady state, short range correlations, short temporal correlations, right? These things live on the scale of a few lattice sites. And the prey need to stay away from the predators need to follow the prey to survive. So you have these correlations, but these are not infinitely range correlations. So it's nothing like a critical point, but these short range correlations induce this very dynamic steady state where dynamics not really ever ceases in a finite system. So this is what happens to the Lotka-Volterra system. And now we're asking ourselves, what happens if we put this in a spatially inhomogeneous setting? But before I get there, I'd like to emphasize again that we have actually 2 types of extinction transitions that we deal with in this business of stochastic reactions or population dynamics or epidemics. One is a set of extinctions which phase transitions that are true phase transitions in the sense that they survive the thermodynamic limit. Right? So in physics, we would define a phase transition as I take system size to infinity, if I do it out of equilibrium, also have to take time to infinity, so space-time system size to infinity. And then I'm tuning parameters. And if I then can switch between, say, an absorbing and an active state, I have a true non-equilibrium phase transition. That one is, aside from finite size scaling, which is in a sense small corrections, largely independent of system size. The transition is there. And in this case, as is generically the case, is described by directed percolation. But then there is also, and for the predator-prey Lotka-Volterra system that happens at large predation rates, there is also total population extinction. So take a not too large system of predators and prey and very efficient predators. So they might be finding all the prey in their neighborhoods and just eat them all. That would not happen in an infinite system, but in a finite system, they can eat them all. When they've eaten all the prey, all the predators can do is go extinct, so you get total extinction. So system reaches the absorbing state in some finite time, which can become very long as the system size becomes large, but it's absolutely accessible in even 100 squared systems if the predation rate is very high. So that's not a true phase transition in the sense that it survives the thermodynamic limit. But it is an actual extinction transition that's really relevant, I think, in lots of biological systems. So we need to be careful about thermodynamic limits. But it's a bit of a different character. And so that happens in finite systems. A finite size effect, if you like, but a very relevant one. Okay, so now we just take, and that's kind of illustrated on this top right graph here. So this is system size and predation probability. So we're having the active state in white, we have prey fixation in blue, and we have coexistence in red. If I'm in a really large system, all I have is a true phase transition separating predator extinction, prey fixation from coexistence. But if I have a finite system, so even with these kind of lattice sizes on a square lattice, make the predation probability really large, I can access the regime of total extinction. And that one is strongly system size dependent, probably exponentially at some point. And so here we have the kind of second transition. So this one is essentially system size independent, modulus and finite size scaling corrections. This one is strongly system size dependent. It's really a finite size effect. So let's stay in the vicinity of this one. So we take a system that has prey fixation, which is, sorry for the change of color coding. Another student a time ago had the prey in green here, not in blue. So it's these. This is prey fixation, no predators surviving in those areas. So we just have a situation where in these areas we have predation rates that are in this regime here, small. And then here we have coexistence. And we just couple them. Couple means they're sitting together in these patches with periodic boundary conditions. And whenever a particle moves diffusively, which is nearest neighbor hopping, into the other domain, it's immediately subject to the different, say, predation probability. So in here, we are subject to a large predation probability, say near 0.4. In here, say it's 0.2. And so as particles move across, they can invade the other regime, right? So predators can invade into the prey regime, but not very far, only to the size of a typical correlation length. That's the usual standard physics situation that you always have when you couple two phases. There is just some kind of typical coherence length, correlation length, penetration depth, whatever you want to call it, and you get an exponential decay typically of the other phase into that system. So just a little bit of boundary effects and that's it. That is what you expect, right? If we do this in this other regime, so now we're going to go here and couple two systems diffusively where we have coexistence in one side and just tune the parameters slightly so we have stochastic extinction, very likely on the other half. And couple those diffusively so we can have particles move between these again. And all we're doing as they move to the other domain, they're acquiring this different reaction probability. So if you do this here, for our predator-prey system, this is the initial state for the stable half. This is the unstable half. This is all on a torus again, periodic boundary conditions. And here we've not changed just for technical reasons, was easier. We not change the predation rate, we changed the carrying capacity. For smaller carrying capacity, the system is stable. For larger carrying capacity, it becomes unstable towards the stochastic extinction events, essentially because the predators with a larger carrying capacity locally find a lot of food that they can take care of immediately. So let's run this. And what you see is as we run this on the right side, we are hitting this total extinction. The predators have overeaten, there's no prey left, and they go extinct. On the left side, we were stable. But then through this diffusive coupling, we generate these linear invasion fronts that go into that unstable system. But you see these invasion fronts go much deeper than a typical correlation length, which is a few lattice sites. Just go completely into it and reset it. Reset it to actually survive and not go extinct again. Same story if we make the unstable system with the same reaction parameters and same carrying capacities a lot larger. So in this second plot here, or second video I'm going to show, we have a twice as large unstable system. If you run that too, now it's just gone extinct. And then at this point here, we are setting off these kind of, planar invasion fronts that come, of course, from left and right because we have periodic boundary conditions, and they run through the entire system and stabilize it. And that's essentially, taking care of a finite size extinction transition and using another finite size effect, namely the influx from the boundaries, to annihilate that. And so as we have that coupling, we're just doing away this kind of large lambda, in this case, transition, and we're just moving the entire system to the active coexistence state. And one way that you can understand this is by looking at timescales. So what we're seeing is we have a more stable and a less stable system. So we have typical extinction times that I'm here plotting versus system size. And the stabler system has a much larger extinction time as function of system size n, typically grows exponential. And the less stable system, that's that blue curve down here, has a much lower extinction time. So what we were seeing above here is we were running the simulation sufficiently long that we are beyond the extinction time of the unstable system, but haven't reached and will not ever reach in the simulations the extinction time of the stable system. So in this kind of shaded area here, we had extinction for the unstable, vulnerable system. But then we have these emanating fronts that run through the system. They move as in mean field theory with a linear speed, so they're ballistically invading and with a constant speed. That speed itself is not the one from mean field theory. It's renormalized by fluctuations and what have you. That's its own little problem, but it is a linear front speed. And so as function of system size, which in 2 dimensions would be the square of the size that I'm looking at in length scale, I get this kind of square root behavior for that front propagation. So this is the typical time it takes for this front to reach through the entire vulnerable system. And so once I'm beyond that, this front that carries with it, activity carries with it both prey and predator particles, will reignite the system, make it active again, re-excite it, and then it's going to be staying excited until maybe at much longer times that we cannot access in the simulations, we hit the extinction time of that larger system. Another way of picturing this is we are resetting the initial conditions in the vulnerable region. Now, this is a stochastic extinction event, right? So we are reaching the absorbing state through stochastic processes. And of course, that depends on initial states. Very importantly, it's all a finite size effect. And so what these correlated initial conditions that are induced by these invading fronts do is they almost ideally set your system to make it as viable as possible. It keeps the predators sufficiently apart from the prey that they're not eating them all, but so there's sufficiently food left for them to survive. It keeps the prey away from the predators so they survive, but doesn't induce huge clusters that would be very vulnerable to direct predation events. So I think what's really happening here is that these kind of invading fronts set up the optimal, almost near optimal initial state to make that vulnerable system survive. That vulnerable system, as you see here, is not actually being impounded its very properties by that stable system. It's characterized by its own fronts, own typical length and timescales. It's just being re-kicked again. So if I made that system much larger and decouple it from that system, we would have exactly these structures. Just with the initial conditions we were choosing, that would not have, just couldn't be set up and survive. And that's what we're regaining here. All right, another example here in the few minutes remaining is the SIS and SIR models. So now we're doing the same kind of dynamics, but in these epidemic models, where for the simple epidemic system, we have infected meets susceptible. So that's like predator meets prey, replaces the susceptible with an infective. That's replacing the prey with a predator. And that's kind of it. And then for the SIR system, we have the infectious also going to this refractive state, inert state R, so they're being taken out of the system, and that just also blocks further dynamics. As I said before, the universality class for the true extinction transition would be different. But now we couple that. So we take a system where we are very finite. So in a finite system, we are prone to maybe see total extinction of the epidemic, so the infectives go away. But we set the left kind of to be more on the stable side and the right to be more on the unstable side. So they're actually kind of both situated near the thermodynamic limit extinction threshold, but the parameters are chosen, really the infection rate are chosen that this system is a little further away. So it's more in the inactive state. And we give it a single seed to start with in both cases, which are these red dots. So blue is all susceptible, red is the one infective. And then if you run this, on the left-hand side, we have infection spreading, just barely, it's a very small system. On the right side, we got extinct. And then at some point, these infection fronts, very noisy objects here, will reach that boundary, will reach across it, and seed sufficiently many active infectious agents on the right side that keeps the system going. And it will not go extinct. It will not go extinct even if we, which happens right now, decouple these systems. So at time step, 3000 Monte Carlo steps, we actually stopped cross diffusion. So whatever was here, keeps going, but there's no new particles that can actually go in there. And you see both of them happily survive. Okay. On the right-hand side, we're going to do something similar, but now with the SIR model. So as I do this, I have R in green. So we have these red guys, that's the infectives proliferating, and they're going into the previously extinct vulnerable SIS region. But at this point here, all the infection in the SIR model has gone down. In the SIR model, in a finite system, you have one infectious front that goes to the system and just seizes because everything is going into the R state or just left with untouched susceptibles, but there's no infectious left. But never mind that there's no more seeding to the right side. The right part of my system has been reignited, re-excited, and keeps going. And that's also true for these cyclic models, but I think I'll just skip that in the interest of time and conclude. With my kind of general input I was emphasizing in the tutorial before that, if you do reactions, population dynamics, and all that, you really sometimes need to absolutely worry about stochasticity and fluctuations and spatial correlations and noise-induced structures that we've seen very prominent in these examples. Of course, don't have to be relevant, but they often are. And I was showing you that it can enhance species diversity in ecosystems and also sadly, revive epidemics through this kind of invasion fronts, which give us a generic mechanism to avoid stochastic extinction or fixation in finite systems with absorbing states. And with that, I thank you all for your continued listening to me and attention.
Let's thank Professor Täuber for two wonderful and insightful talks. I May I ask the first question? So in the last example you showed, on the right panel, so yes, this one. So why is there no recovery species like on the right half of the?
Oh, we just had an SAS model coupled to SIR.
Oh, okay. I see.
No, that cannot be. You can also do SIR with SIR, and then you just inside a single epidemic front that goes to there, and we're done with it. You can do all these things, yeah.
I see. SIR
I
versus
didn't say
SI.
that clearly, so thanks for following up, Jing.
Okay, so we have some questions in the chat. So Ashok, would you like to unmute yourself and ask? I think you're the first one who asked the question to the research talk.
Sure. Yeah, great talk away. I had a very I've been always wondering, are there any effects that space have on noise that are, maybe not just the effect of density? So it's a peculiar question, I know, but I wonder if you've thought of that.
So you said, does the size of the simulation box matter? Yeah, okay. So first of all, once your size of your simulation box gets smaller than the structures you're forming, then you're effectively in 0 dimensions back. And that tends to make the system more vulnerable towards extinction. That is something that, Mobilia and Fry have studied 10 years ago very carefully for these rock, paper, scissors systems. And so the crucial bit is once you have spatial system, it's like really introducing a lot of chances to survive by evading dangerous regions. And that requires the presence of these fronts. And when these fronts are too small, then it's essentially 0 dimensional. So that's the first rule. So you need to be on a system size that's large compared to these intrinsically generated fronts, and how large they are depends on the reaction rates and diffusivity and all that. So that's a crucial one. Beyond that, there's a lot of additional kind of more subtle effects that we're still trying to figure out, honestly. So great question.
What about the other limit when the system is much, much larger than the size of the clusters?
Then I think that's it. We don't see much dependence at that stage anymore.
Okay.
That would, I was talking about these kind of statistics, vulnerable systems, vulnerable to stochastic extinction. When you're in that regime, you're safe.
So the next question is from Steffi Jose. Would you like to unmute yourself, Steffi?
Hey, thanks for the wonderful talk. So, I have a very basic question. Like, how much does the details of the microscopic model really matter? So, in the tutorial talk, you showed a slide where, like, a conservative model shows clustering, very typical clusters, while a non-conservative model showed spiral structure.
Right.
And
so, yes, so great question. And I was rushing through it. So I'm really happy to go back to this. So in the details that do not matter is the order in which you do these processes, and maybe some other kind of funny things. But conservation laws are not details. Conservation laws are kind of crucial ingredients to your system. And I'm not talking about mean field correlate conservation laws, right? Not kind of artificial, accidental conservation laws that show up in an approximation, but real ones. So if the total particle number is conserved, that means once I go to the kind of eigenmode spectrum of what is in there, there's a diffusive mode running through the system. And that diffusive mode is mixing. And that can actually destroy, it's a bit subtle, but it can actually destroy these spirals. And that is what's happening in this conserved rock, paper, scissors system. When you do May-Leonard, you're destroying the conservation law. So it looks like a harmless change, but you're really changing an actual conservation law that is true for the fundamental stochastic dynamics, not just kind of for some, effective description. And those really do matter. That's a microscopic detail that is not a detail, but absolutely matters. And we are only in the process of figuring all these out. Yeah, so conservation laws very clearly matter. What else? We'd love to know. But conservation laws absolutely have to worry about. So that's a microscopic detail that is totally crucial. Never ignore conservation laws. And it has this really striking macroscopic consequence for the pattern formation in this cyclic competition models. So great question. Thank you, Steffi.